Hello, my name is Michael Baratko, and today I will discuss our work investigating the representational capacity and bias in a number of geometric embedding models commonly used to represent directed graphs. In this work, our focus is on the task of directed graph representation. Given a directed graph, we wish to learn a parameterization of its nodes, which, for a given energy function, encodes the probability of edge existence. As our graphs are deterministic and not weighted, we make a hard decision on edge existence by using a global threshold on the energy, and evaluate using F1's score. Various choices of parameterization have been explored, often motivated by geometric intuition. Our fundamental question, therefore, is to determine how the choice of parameterization may impact the ability of a directed graph to be represented, both theoretically and empirically. The most obvious approach would be to represent the nodes as points in Euclidean space, using their distance as the energy function. As this energy function is symmetric, however, it can only hope to represent undirected graphs. It was known as early as 1984 that any undirected graph can be embedded using this approach. Inspecting this thresholded distance, it was observed that the edge existence corresponds to sphere intersection, motivating the definition of sphericity, which is the smallest dimension a given undirected graph can be represented in using sphere intersections. Quite similarly, the boxicity of a graph is the smallest dimension a given undirected graph can be represented in using a set of overlapping boxes. It was proven in 1969 that any undirected graph can be embedded in this manner in dimension at most half the number of nodes. Note, however, that boxes require 2 parameters per dimension, so this may require the same number of parameters as the previous vector representation. Returning to vectors for a moment, another natural choice for the energy would be to consider using the dot product, which amounts to factorizing the adjacency matrix. We know using the same vectors for rows and columns will lead to a symmetric matrix. However, it's worth noting that any undirected graph can be embedded in this way with dimensionality less than or equal to the number of nodes. In matrix factorization, a common approach to avoid the symmetry constraint is to simply use different representations for the rows and columns. Concatenating these row and column representations for each node, this can be viewed as a directed graph embedding with the following energy function. Note that one can consider embedding the associated undirected graph where each node is replaced by separate in and out nodes. The previous theorem therefore implies that any directed graph can be embedded using this similarity model in dimension at most twice the number of nodes. We can leverage this approach to extend any symmetric energy function, such as the aforementioned distance function, to an asymmetric variant capable of modeling directed graphs. Interestingly, these two approaches have roughly equal representational capacity, which is quite different than the undirected case, where distance may require arbitrarily more dimensions than dot product, and thus shows the importance of considering the directed case explicitly. The reason for this difference is that we only compare in and out representations for the directed graph, and thus only observe half the adjacency matrix for the associated undirected graph. It is therefore of interest to consider approaches which inherently model directed graphs, as they may be able to do so with far less dimensionality. Inspecting the forms of the existing energy functions immediately suggests 2 obvious generalizations by replacing the fixed matrices with learned weights. Observing that each model is a generalization of the other yields the displayed relationships for graph representability. Thus, for vectors we have a theoretical understanding of their representational capacity and bounds on the dimensionality required for this representation. In addition, it has been shown that there is a trade-off between dimensionality and precision, which has been investigated rigorously for vectors as well. Our work addresses each of these aspects for box representation, putting them on equal theoretical footing as vector models. Specifically, we ask if boxes can represent any DAG. If so, in what dimension? And also investigate the precision required, not only for theoretical reasons, but also to determine if the representation is robust to slight perturbations of the parameters, as would be observed frequently during gradient-based training. This last point also raises the issue of whether the representation can actually be attained in practice. A question which is relevant not only for boxes, but also for Euclidean and hyperbolic vector models, for which the constructive proofs of representational capacity are not in line with the common method of training such representations via gradient descent. This is most poignantly captured in Poincare embeddings, for which a construction by Sarkar shows that it is possible to embed undirected trees into the Poincare disk with arbitrarily low distortion. This is beautifully visualized on the Hyper-E website, where it is contrasted with an optimization-based construction. While the two approaches result in very similar embeddings for this toy example, the construction is clearly not the same and may generally result in very different representations. While these approaches focus on undirected graphs, Nickel and Keela suggest that edge direction can reasonably be decided on by use of the Euclidean norm, where parents have smaller norm than their children, and combine this with the hyperbolic distance using the following score function. Unfortunately, training directly with this score did not yield positive results. To understand why, we picked an arbitrary node and plotted the score relative to this node for all points on the Poincare disk. We note that while this does seem to pick up some desired child nodes, it also picks up nodes on the opposite side of the disk. With this awareness in mind, we defined an energy function for a hyperbolic model which is capable of representing directed graphs. Here, f beta is a mapping to the hyperboloid, and d squared is the squared Lorentzian distance as recommended in Law et al. 2019. As depicted on the left, the resulting energy seems to have the appropriate geometric bias for directed edge representation. To evaluate whether each of these models is capable of attaining their full representational capacity, we performed the most comprehensive empirical evaluation of graph embeddings to date. Considering 10 of the most relevant graph embedding approaches, we evaluate on both real-world graphs as well as hundreds of synthetically generated graphs using extensive Bayesian hyperparameter optimization to ensure each model is tuned appropriately. We now discuss how probabilistic box embeddings can be used to represent a directed graph. A box is a Cartesian product of intervals for which the volume and intersection can be easily calculated using min and max functions. Box embeddings are trained using a probabilistic interpretation, which is possible when the boxes are embedded in a space with finite measure, such as the unit cube. Here, the marginal probability of being an author is given by the volume of the author box, and similarly, the probability of being a biologist is given by the volume of the associated box. One can also calculate conditional probabilities, for example, the conditional probability of being an author given that one is a biologist. This latter property was leveraged in the original work to represent knowledge graphs, particularly transitively closed ones. Edges, in this case, were represented by box containment, which is motivated both by a natural set-theoretic Venn diagram interpretation as well as a conditional probability interpretation. For example, the probability a dog is a mammal is 1. While originally applied to trees, there is nothing preventing this approach from modeling graphs where nodes have multiple parents. We can, of course, take the negative log probability as our energy function. A minor point, which we will return to later, is that boxes have undergone various training improvements over the years, with the most recent approach modeling the coordinates of boxes as latent random variables. Thus, it is necessary to take the expectation of these random variables when calculating the volume. We turn now to the theoretical results, starting with the question of whether boxes can represent any DAG. In this work, we prove the answer is yes, and we'll give a quick sketch of the proof here. Just as many fundamental results about vector representation rely on the concept of sphericity, the proof fundamentally relies on the analogous concept of boxicity mentioned earlier. Given a graph G, we construct GU to be the undirected graph obtained by ignoring edge direction. Results on boxicity imply that this graph can be represented as a set of overlapping boxes. Thus, the only remaining task is to decide edge direction. To do so, we topologically sort the nodes in the DAG, and extend the boxes in the new dimension such that they have decreasing volume according to this topological sort. For details as to why this is always possible, please refer to the detailed proof in our paper. Now that we know that boxes can represent any DAG, the natural question is, what dimension is required? An immediate consequence of our proof is that DAGs can be embedded using probabilistic box embeddings in at most one more dimension than the boxicity of the graph ignoring edge direction. Thus, any result on boxicity can extend to a dimensionality bound for probabilistic box embeddings. Specific bounds involving characteristics of the graph are available, but the best general result proves that the boxicity of a graph is bounded by the max degree times log of the number of nodes, and thus the bound for directed graphs is 1 greater. This gives us a very reasonable dimensionality bound, and so we turn to the question of precision. As mentioned previously, it is important to prove that a model is not exploiting precision as a way to reduce dimensionality. We prove that box embeddings for a graph are attainable in both reasonable dimension and precision. The proof essentially amounts to a more careful construction. Given a graph, we obtain a boxicity representation with bounded dimensionality. We note that only the order of the endpoints is required, and replacing endpoints by their integer rank will not change the overlaps. This requires a logarithmic number of bits per dimension, which provides our bound for the boxicity portion. We calculate a viable threshold tau based on the possible box sizes such that the height of the boxes in the new dimension are tau to the k. This can be accomplished with k less than the depth of the graph, which provides the following bound, and yields the desired conclusion. Hence, we find that boxes have reasonable precision, leaving only the empirical question of whether these representations can actually be attained in practice. Turning to the empirical results, as mentioned before, in addition to 4 real-world graphs, we have also evaluated over 5 families of synthetic graphs with a variety of parameter settings. To remove as many confounding factors as possible from our analysis, we perform Bayesian hyperparameter optimization for each method and over each family of graphs, and report the evaluated results using these optimal hyperparameters. To compare models fairly, rather than dimension, we compare using an equal number of parameters per node, evaluating each with 8, 32, and 128 parameters. We observe that in low dimension, the embedding methods with more geometric structure, including hyperbolic and boxes, tend to outperform vectors, but in higher dimensions, this no longer holds. This tendency has been noted previously, where, despite outperforming in low dimensions, geometric models quickly reach a saturation point, while vector models can continue to improve with additional dimensionality. What's puzzling, however, is that we know, at least for boxes, the model is capable of representing these graphs exactly, and thus the limitation must be one of training, not of representation. In the seminal work on box embeddings, it was noted that while the calculation of volume and intersection of boxes is straightforward, the prevalence of max and min functions result in zero gradient for many settings of parameters. In particular, when boxes are disjoint, their intersection volume is zero, and the fact that the volume is a product means that this is even more problematic in high dimensions. In subsequent work, this was mitigated by modeling the box endpoints using Gumbel random variables. Here, LSE refers to log sum exp with temperature beta, which corresponds to the variance of the underlying Gumbel variables. This approach resulted in smoother loss landscapes, as the use of random variables to model endpoints meant that any given configuration of boxes has some positive probability of occurring, solving the problem of zero gradient in the case of disjoint boxes. On the other hand, this also changes the representational capacity, as the expected volume of the intersection of boxes will always be positive, an assumption not made during the proof of representational capacity. Higher temperatures lead to smoother boxes, and as the temperature goes to zero, we recover the original box model. This temperature is tuned as a hyperparameter, however, and thus the global level of uncertainty is fixed for all boxes throughout training. Our solution to this problem was to develop a more flexible model which could capture both the ease of training provided by Gumbel boxes, but also learn to be disjoint as in the original hardbox model, which we knew was representationally capable of modeling any DAG. We do so by taking a pragmatic approach, replacing each max operation in the original hardbox model with log sum exp, and rather than tuning these temperatures as hyperparameters, we train the temperatures as free parameters of the model. Doing so enables us to use separate temperatures per dimension and even per entity by taking an average of temperatures when computing intersection. Once again, as temperatures go to zero, we recover the hardbox model, the distinction here being that since these temperatures are trainable, the model can actually realize this in practice. Our intuition suggests that high temperatures would be valuable at the start of training, when many boxes which need to intersect are disjoint, and that temperatures should decrease over time, allowing for additional sparsity. And indeed, we do observe this in practice, even without explicit regularization to encourage it. While not strictly speaking a variance of sorts, the similarity of these temperatures to the variance in the Gumbel box case suggests the loose interpretation that the boxes start fairly uncertain of their position and become more sure of it over time. Our previous observation was that geometric embedding methods reach a saturation point after which they are not able to take advantage of additional dimensions. However, for T-box, we seem to capture the best of both worlds: increased performance similar to geometric models in low dimensions, and the ability to effectively make use of additional dimensionality, providing us with the empirical validation that boxes can represent any DAG in practice. With the wealth of empirical evidence available to us, we were able to perform ablation studies and draw conclusions about the inductive bias present in various geometric models. As mentioned previously, there are many choices for how flexible the trained temperatures should be. We explored a number of options and found that for equal dimensionality, adding additional flexibility always helps, with the per node per dimension temps optimal. By performing such a large-scale evaluation, we can also confidently make claims about the inductive bias which each model exhibits. For example, we see that in low dimensions, boxes tend to perform better than hyperbolic embeddings when modeling transitively closed graphs. While for non-transitively closed graphs, hyperbolic performs better than box, which performs better than order embeddings. To further investigate the correlation of a particular model's performance with respect to various graph characteristics, such as clustering coefficient or flow hierarchy, we can inspect parallel plots which show the relation between various graph characteristics and the difference in a model's performance. Here we see that boxes are more suitable than hyperbolic when the clustering coefficient is large, for instance. We include a large number of such plots in the appendix and also will release the dataset for additional exploratory analysis. In conclusion, in this work, we proved that box embeddings can represent any DAG and introduced a novel trainable temperature variant of box embeddings which is capable of attaining these representations in practice. We also demonstrated that various geometric embeddings carry predictable biases based on graph characteristics by conducting a rigorous large-scale evaluation of many graph embedding models, which we hope will be a useful contribution to the community. Thank you for your interest.